Hello everyone. So in this video, we will be solving some more problems on finding the image and the matrix of a linear transformation. But now we don't have a standard basis on hand, but we are given the image for some random vectors, or we are given the image of an ordered basis for R3. Like you see here, these are not the good old 1, 0, 0, 0, 1, 0. They're different. So how do I find the matrix A of a linear transformation if I'm not given the image of the elementary vectors? If you recall the change of basis matrix from chapter 4, I have a video posted on YouTube, or you can read my lecture notes. And that's the concept that we'll be applying. That or the theorem above that we do not need to prove. Now, I have an ordered basis, let's call it B. So I have an ordered basis B, which is consisting of the three vectors, ordered basis B with three vectors. I have -7, -4, and 6. And I have 4, 2, 3. And the good thing is, in this question, you don't have to calculate the image. They're not giving you a formula. They have already given you the image of each of these vectors in the ordered basis B. So if this is V1, this is V2, this is V3, I already have the image of each of them under the linear transformation L. Now, what is the catch here? This linear transformation is still picking a vector from R3 and giving you an image in the two-dimensional subspace, right? As you can see, I only have two components here, but it's picking up a vector which is represented with respect to basis B, and that's something we don't want. So how do we change from basis B to a standard representation, standard basis representation? We apply the change of basis matrix. So this is how you calculate it with one step. You multiply by the inverse. You combine these vectors, find its inverse, and multiply the image which is represented as with respect to the coordinate basis B, and you multiply it by the inverse, -3, 1, -1, you get -7, -4, 6, 4, 2, -3, inverse, and that would be the matrix of your linear transformation. 3, 8, 8, 8, 7, 3. You could do this, you could convert each vector, because once your linear transformation finds the image of this vector u is represented with respect to basis B, it finds the image of u, but that image is also represented with respect to basis B. So you could convert the coordinate vector separately or step by step for each v1, v2, v3, or you could combine them together and multiply by the inverse. And that's the final answer. Good. Let's do one more example. We'll apply this theorem. And now what is happening is my linear transformation is picking up a vector from the domain which is represented with respect to basis B, and it's giving me an image which is not in terms of, is not represented with respect to B, but rather is represented with respect to a different ordered basis C. So let's just try to understand quickly how is this question working? I'm given I'm given an ordered basis for R cube, an ordered basis for R square, and I'm given the formulation of the linear transformation here, right? Let's just understand how this linear transformation is behaving here. It's not similar to what we saw in the previous video. Now, again, my domain is still R3 and my codomain is still R2, but the representation of each vector is affected. So I'm picking a vector in R3, which is represented with respect to basis B, because that's what we are dealing with. That's understood. In every question you see on the exam or homework, if you see an ordered basis and I'm picking the vector from my domain with the given ordered basis, that's understood that that vector is represented by that. And now the catch is, I apply the linear transformation formula, get an image, but that image of that vector is represented with respect to the ordered basis C. It is very useful computationally for different streams of advanced mathematics, but we want the standard matrix of linear transformation. Now, how do I find that? We apply the theorem above. Now we're doing a change of coordinate basis, but not with respect to B. We are changing from C to the standard basis, right? So that's something we should be careful about. Now we are changing the image, not from B, but to C. So we'll just keep it simple, straightforward, and the matrix of transformation, let's just denote the matrix B by that. So I'm going to combine all the vectors in the ordered basis B, 9, -5, 5, 1, 2, 9. And let's just combine all the vectors in the ordered basis C, and let's just call it C tilde for the matrix. Now in this case, they haven't made your life simple. They just don't give you the image of each vector in the ordered basis. They give you a formula for the linear transformation. So you have to find the image of each V1, V2, V3 in ordered basis B and find its image with respect to the ordered basis C. So let's just quickly simplify that. So I want to find the image of each vector, and I've got the first vector is 5, -3, 2. I plug it in the formula. I've got -3 times 5 plus 6 times -3. I'm only going to expand the first calculation, and the rest follows similarly. So I've got 5 times x1 negative x2 -9 times x3. And when you simplify that, you should get -15 and 10. Same thing you'll do for the second vector in your domain, second vector in your basis, B. And when you do that math, it should be -12 and 5. And the last step, you find the image of the last vector in your basis B, and that would turn out to be 90 and -78. Now keep in mind, all these images are here in the codomain. So all of these are represented with respect to basis C now. So I'm changing, we're again using the change of basis matrix from chapter 4, but now we're changing from basis C to the standard basis. So what is the formula for that? So my A will be, in this case, I will do C tilde inverse and multiply by the image of each vector. So 5, 90, negative 78. And you know why I'm multiplying by the C inverse on this side? Well, you recall a few concepts of matrix multiplication. The multiplication should be well defined, right? Now, what is the inverse of C tilde? You could use a calculator for that. I replace these two and I change the signs and I do 64, negative 64, positive 63. I've got 1 over negative 1. So when you multiply that, multiply C inverse with this matrix, that will give you the final answer. I'll just write it out here for you. And I've got 30, negative 25. I've got 51, negative 44. And I've got negative 18 and 6. That's my matrix of linear transformation with respect to the standard basis. And that's how you solve a question like this. And next we'll move on to more properties of linear transformation in the next video.